Okay, example problem number 4. Again, circular motion, but this time it's not gravity that causes an object to go in a circle. This time, kid is wheeling a rock around on a string. So it's going to be the tension in the string that is going to be the centripetal force for the most part here. Okay, so again, the important thing to recognize is the centripetal force. The centripetal force is something else. Here it might be the force of tension. Earlier it was gravity. It could be the force of friction. It could be the normal force. It could be some. The centripetal force is whatever force towards center. Whatever it is that's making it go in a circle. It's not a real thing. It's just some of the force becomes a centripetal force. All right, so what do we got here? A 500th kilogram rock is at the end of a string and is being wheeled around in a clockwise vertical circle at constant speed. The diagram above shows the stone at the highest point and at the lowest point. The circle has a radius of 2 meters and a period of 2 seconds. So those are the important things. Radius of 2 meters, period of 2 seconds. That means it takes one trip takes 2 seconds. So they want to know the speed, the translational velocity. That's the velocity through space. Translational velocity. Velocity is the distance it travels and the time. In this case, the distance it travels will be the circumference of the circle divided by the period. Actually, I should properly label that the period. Capital T. So 2 pi r over the period, which would be 2 pi radius 2 meters over a period of 2 seconds. Well, that is super easy because 2 cancels out with that 2. We get meters per second, and 2 pi meters per second. Well, 3.14, we're going to go 6.28. Velocity equals 6.28 meters per second. That's pretty simple. Now, determine the tension of the string when the rock is at the top and when it's at the bottom. So when it's at the top, here, this is kind of interesting. We should take a moment to draw this. When the rock is at the, well, we just have to think about when the rock is at the top. Let's say the rock is here at the top. There'll be force, tension, and you have to deal with, you still have gravity. So those two forces combine become the centripetal force. So the centripetal force is the force of tension and the force of gravity because those are both towards the center. So mv squared over r equals the tensile force plus mg, the weight. mv squared over r, 0.05 kilograms. V squared, 6.28 meters per second squared over r, 2 meters? 2 meters equals the force of tension plus 0.05 kilograms times 9.81 meters per second squared. So we'll know everything but the force of tension. We can solve for the force of tension. This is when it's at the top. So we do some arithmetic. 0.05 times 6.28 squared divided by 2. We get, what do we get here? 0.98596. Should we run it? So we'll call it basically 0.99 newtons equals the force of tension plus 0.05 times 9.81, 0.49. 0.4 newtons. All right, so to find the tension at the top, bring this over here. We're going to subtract 0.99 minus 0.49. Force of tension is 0.5 newtons. That's at the top. At the bottom, a little different. This is interesting. When it's at the bottom, a little different. Think about the free body diagram when the rock is down here. Gravity is down, but the tension is up. So now this is a little different. Just a little different. The centripetal force equals the tension is up, but gravity is down. It's not the sum. It's not, those two are not both in the center. It's going to be the separation. It's the difference between them here. So only the force in the center, right? This has to be so much greater. When it's at the bottom, if you've ever whirled something in a circle, the greatest tension is not at the top. The string almost, if you're not wheeling it fast enough, the string will go slack and no longer keep a circular motion. So the tension is going to be greater. So what you're going to end up here is going to end up with the force of tension to not be here I didn't write it out. I should have written centripetal force equals the force of tension plus the force of gravity. And so the force of tension was equal to the centripetal force minus the force of gravity. That was our equation here. Here we're going to get the reverse. We're going to get the force of tension to be equal to the centripetal force plus the force of gravity. Centripetal force is still the same, mv squared over r, which we figured out that was 0.99 newtons. The gravity is still the same, that we figured out before, 0, right, little mg, which we figured out was 0.49 newtons. So the tension force will be 0.99 plus 0.49, 1.48. So at the top, at the bottom, a little different. That should be familiar to you if you've ever whirled something around. There's going to be more tension keeping it to go in a circle at the bottom than at the top.